Hi and welcome everyone. I hope you all enjoyed the online version of Hacktivity so far. In the next 40 minutes with my colleague Albert, we will talk about how to reverse engineer Go binaries with Ghidra. First, let me quickly introduce ourselves. We work at Kujo AI, a network intelligence software company, in its fairly young security research team. Previously, we both worked in financial and security companies as well, where we gained experiences in various fields of security research and operations, such as incident response, memory forensics, malware research, and reverse engineering. We both have some experiences with talking at conferences or giving lectures, but this is the first time that we had to do an online pre recorded version of our talk, so please forgive us if it's not perfect everywhere, but we tried our best. Now, Albert will start with the background of our research and an introduction to the difficulties of reverse engineering Go binaries with Ghidra, which I will follow with explaining the problems that we investigated and the solutions that we created for them.
Before we jump into the nitty-gritty details, we wanted to share why we had decided to go with this topic. So, recently we have seen a shift in malware development in terms of their programming language, as more and more malware is developed under Golang. We came across some issues when we started to analyze such binaries. For example, Golang files have huge file sizes. Disassemblers handle Golang strings unusually, and finally no symbol names are available due to stripping. Ghidra, a open source disassembler, for example, it's still in its infancy phase, so basically only a few open source scripts have been made available to tackle this problem, but none of them seem to work consistently. Our goal was to make Go reversing with Ghidra easier, and in order to achieve that, we had to understand Golang and how it's different from other languages, but also to get familiar with Ghidra as well, and finally to create some scripts. Some basic information about Golang. Golang is a open source programming language designed by Google in 2007. It was made available to the public in 2012, uh, and its current version is 1.15. In a recent survey on GitHub, it was revealed that Golang comes out top of the languages most developers want to learn. Golang has a couple of advantages over other languages, like it has a simple and clear documentation. It's very easy to learn. Basically, it supports multi-architectures like Windows, Linux, macOS. It has good scalability and it has an inbuilt garbage collection system. We wanted to quickly highlight the fact that there's a noticeable shift on the malware landscape. Go binaries are growing by the numbers, and this trend will eventually continue in the future. The rate in which they are found suggests that this is only the beginning of the Golang malware surge. Some of the more interesting Go malware families that have been observed in the past year are IRC Smoke ransomware, Kaiji, FritzFrog, Ecoriax, IP Storm, LiquorBot, and GoBrot. LiquorBot is basically a re-implementation of Mirai in Go. It was first discovered in May 2019, and basically it was targeting small office home routers. One of the initial vectors, it was brute forcing SSH logins, but it was also had capability to install a Monero mining software. LiquorBot is also cross-compiled for ARM, x86, x64, and MIPS architectures as well. The next interesting malware family is IP Storm. It was first found in June 2019, and it is obviously also written in Golang. Its first versions were basically targeting only the Windows platform, but later on the developers decided to include support for Linux and Android as well. The initial attack vector, again, is SSH brute forcing of weak credentials. And IP Storm also had some ties to IRC Flu, another brute forcing botnet. So it's quite likely that the developers are the same for the both botnets. IPFS is a peer-to-peer protocol, and IP Storm uses the PubSub network as well. The infected hosts are acting as SOX5 proxies, and we observed many iterations of versions for IP Storm, which would mean that it's under heavy development. IP Storm, instead of a mutex, uses the package called single, which is simply acting like a log file. The next interesting family is EchoRex. It's a ransomware which was first discovered in June 2019. It is targeting specifically one type of devices. It was the QNAP NAS devices. And again, it was using some brute forcing techniques to gain foothold on the device. At the beginning of June 2020, a new wave of attacks was observed for these QNAP devices. And finally, later on, a decryptor was also released. FritzFrog is the next interesting malware family. It was first of a kind because it's a peer-to-peer botnet, which was first discovered in January 2020. Again, as we have observed before, these are mostly targeting SSH servers, and they are trying to brute force the weak credentials. It had a modular setup, which meant it was easily pluggable by other plugins as well. It was multi-threaded and basically a fileless malware. It had used a custom peer-to-peer protocol. It was also listening on port 1234 and waiting for comments from the server. It also included a Monero mining capability, and finally it successfully breached more than 500 servers, targeting government, education, finance, and other sectors as well. And our last interesting malware family is Kaiji, which gained attention because it was named after a famous manga series. It was fully written in Golang from scratch. Kaiji spreads again by brute forcing SSH login credentials on specific IoT devices. It had a few capability and features, like it would get installed into specific Linux folders under specific fake system process names like netstat, ls, or ps. It also had capability to set up persistence under profiled, initd, systemd, and it would write itself into crontab too. Kaiji copies its rootkit module to a specific location and basically runs itself every 30 seconds. Attack-wise, it has a couple of implants, like DDoS implants. It had capability to launch TCP fluid, UDP fluid, IP spoof, and specific other fluid types. It had capability to initiate a SSH brute forcer as well. It had a list of hard-coded passwords and IP ranges to attack. And one other interesting facet of Kaiji was that it used a specific host rewrite for the Quad 9 DNS resolvers. Perhaps the developers were testing this specific feature because in its current state it wouldn't make much sense. And now let's find some ways how we can identify malware as Go binaries. First, you could simply look for the string Go build ID inside the binary. But oftentimes you will find references to golang.org as well. The PDB path usually references /go/source. Another clue is having symbol names starting with .main, .runtime, or even .os. But also section names like go symtab or go.buildinfo are also seen. You could simply use the Linux tool called file, which displays the Go build ID as well. Finding the Go compiler version is not that easy. The function which stores the compiler version is runtime.buildVersion. One way is to list the strings of the binary and then grep for go one dot. But obviously this method will be deprecated as soon as the Go compiler version hits 2.0. So instead, let's find the symbol build version using the tool nm. The data stored at that address is not readable, so it could be pointing to another address. We are reversing the order of the hex values here, and that reveals the correct address at which the compiler version is stored. Go binaries are always statically linked, and all the necessary libraries are included in the executable. The large size of Go binaries presents some interesting challenges, like malware distribution is difficult with binaries that are around 2, 3, or 4 megabytes. Antivirus products might have issues scanning through the whole file properly. And reversing such large files is time consuming. And however, Go binaries present no dependency. So let's compare two simple hello world programs. One was written in C and the other one is written in Golang. And after compiling, the difference in size is remarkable. Also note that these are unstripped binaries. After our hello world programs are put in Ghidra, the first thing we spot is that the C program has 18 functions recognized by Ghidra. The Go program's disassembly is more hectic. Almost 800 functions. 1800 functions are recognized. Fortunately, this program has all the debug information and symbol names, so it's easier to navigate through the myriad of functions and understand what the program's purpose is. Unfortunately, reversing binaries is not always fun. When compiling binaries, you have the option to discard symbol names and debug information, often to spare size and hide valuable information to understand the deeper workings of the binary. This presents challenges to reversers as function names, variable names are not present anymore. Reversing such files requires certain experience, creativity, and plenty of time. So let's see the previous scenario again, but now with stripped binaries. We are using the strip -s and -ld flags parameters to strip any information from the binary. The size difference again is huge. Putting those files into our favorite disassembler reveals that the C program has 15 functions recognized by default. The Go binary again has a large function count, but this time we have no clue as to which function does what. Malware binaries are usually like this, and it's always a real challenge to get to the bottom of their intentions. The main function is easily located in unstripped executables. This is where the program starts via the entry point. However, the disassembler can't identify the main function in stripped C binaries and randomly assigns a function name to it. Unstripped and disassembled Go binaries have the main function as seen on the picture here. But note that the missing main function name here on the second picture uh, when we try to analyze and disassemble a stripped Golang binary. The function name is random as Ghidra cannot really identify without symbol information. And now I will pass the microphone to Dorka, who will present how we can recover symbol information in Go binaries in order to beat these previous issues.
Let's see if we have any chance to recover the function names. As a first step, we simply checked the strings within the Hello World binaries and searched for the function names within the original and the stripped versions. As you can see on this slide, the function name main was removed from the stripped version of the C Hello World binary. Meanwhile, the main.main function name is still visible in the stripped Go binary, which is very promising. So we looked at the same within Ghidra. Here, just below the main.main string, there is another function name, which is also a very positive sign. So we opened up the memory map to find out where these function names are exactly located within the binary. We found this Go specific section called Go PCLN tab. So as an obvious step, we wanted to understand how this section is built up, what kind of information is stored there. So we simply searched for it. Luckily, there is a detailed documentation available about the PCLN tab structure, and we won't go into every single detail of this PCLN tab. We will only focus on the parts that are important to recover the function names. It starts with a specific header. There is a magic value in the very beginning, followed by other important information. And then there is the so-called function symbol table. This table contains information about every single function within the binary. First, there is a pointer to the entry point of the function, and then there is an offset where the function metadata table can be found. Just before we go into the details, what can we see within the metadata table, I would quickly touch on the case of Windows executables. During our research and during this presentation, we used Linux binaries. So here I would like to highlight a little bit of the differences within the Linux binaries and Windows executables. Here, as you can see, there is no section called Go PCLN tab or something like that. Rather, we have to look for the PCLN tab structure, which is located here in the R data section. And luckily, this is not too difficult since we know how the structure is built up, we know how the header should look like, what is the magic value. So it just adds one extra step to our script. It's easier in Linux because we just need to look for the section name, but it's obviously not that difficult for Windows either. So let's turn back to the metadata table. It starts with the same value, the address of the entry point of the function, and then there is an offset to the function name, which is exactly what we need. We have to know where the function starts, and then we have to find somehow the name of the function. And as we can see, we have all this information here. So the steps of the function name recovery are very easy, and this is what our script is doing. We locate the PCLN tab structure, then we extract the function addresses, and finally, we need to find the offsets of the function names. If someone wants to go through step by step how to calculate these locations, you can find all the details on this slide. So in case of the stripped Hello Go binary, if we execute our script, we can see that the functions were renamed. We can even find the main.main function. And as a cherry on the top, there are even more functions defined after the script execution. In case of a real-world example, this is the Acorix ransomware. We can see that this very simple script can help us a lot during reverse engineering. We have all the function names, searching for the main functions. We can quickly have some idea about the purpose of the malware, which makes reverse engineering much more faster. We don't have to go through one by one in like for 2,800 functions. Rather, we can just look for the interesting function names. Obviously, there were some challenges when we created our scripts. One of these challenge was when Ghidra couldn't, for some reason, couldn't define the function name string, because in this case, when we want to retrieve the function name, our script won't find there any strings, but it can be solved easily, because if we cannot find the data that we are looking for first, then first we try to create the string and then rename the function. So it's not a very big deal, but we still have to handle this issue. The other challenge is not related to stripped binaries, rather how Ghidra uh, analyzing Go Linux binaries. So when we load a new Linux Go binary within Ghidra and then the auto analysis is running, then it will rename some of the functions to an incorrect name. So as you can see here, there are many functions called reflect dot. So basically only the package name is visible and we cannot really see the actual function name. But luckily, according to the developers, this problem will be solved in the next release. So now that we talked about how to recover function names, let's turn to another issue that we were working with. It's how the strings are defined within Go. So if we look at the Hello C and Hello Go examples again, we can see that there are 70 defined strings within the C binary, while there are more than 6,000 within the Go binary. On one hand, if we don't really know what we are looking for and we just want to go through all the strings, that can be more difficult to go through 6,000 strings. But what is even worse, that if we look for the activity string, it cannot be found within the defined strings in the Go binary. In C, it's very easy. We can see there is the hello activity string, while in Go, we don't find anything. There are 6,000 strings, but still no activity. So let's see what happens if we use the strings utility. In C, this is what we would expect. It's very easy. We get our string. But in case of Go, hello activity is the part of a huge string. Now it's not that difficult since the hello activity is at the very end of this string, but it can be somewhere in the middle, so it can be difficult to find. So why is it happening? Why do we see these? While we are used to the C strings, that these are sequence of characters terminated with a null character, it's very easy. This is what the strings utility is looking for. But in Go, strings are defined in a different way. These are sequence of bytes with a fixed length, and there is no null termination. So there is a so-called string structure, which consists of a pointer to the sequence of bytes, which is our string, and an integer, which is the length of the string. And these smaller strings are concatenated together to a huge string blob, and there will be maybe one null termination character at the very end, but between the specific strings there is no null character, and Ghidra has a hard time defining these strings within Go binaries. So the idea that to create a script where we help Ghidra to find these string structures. Obviously, there are many, many different ways how these string structures can be created. They can be dynamically or statically allocated. These are different per architecture thanks to the different instruction sets. There can be even within one architecture different solutions. And we cannot forget about the possible changes per Go versions. We, in our test, used Go version 1.11 and above, and for those our scripts are working. So now we will go through some of our solutions, and let's start with the dynamically allocated string structures. There will be several scenarios that we will talk about. Here we can see a hello world example of C. Just quickly, it's very easy, 6 lines, there is the string, it's visible. And comparing this to the Go hello world example, we can see that the function looks more complicated. We don't see the string that we would expect. So we have to spend some time to understand the structure, how it is built up. But luckily, it's not that difficult to find the data that we are looking for. So it starts with putting the address of the string to a register and then placing this in the stack. And finally, we also put the length to the stack. What you can see on the right side is that this string is not defined. This is why we couldn't find among the defined strings within Ghidra. So the idea of the script is to search for these instructions and use this information define our strings. We can see the 32 and 64-bit versions, not really different. So as we already talked about it, first the address of the string is placed into a register, and then this is placed to the stack along with the size of the string. So if we execute our script, we can see that now hello activity will be defined, and it will be much easier to read the assembly code because we can see the string that we are looking for. And in case of the ransomware example that we have seen before, you can see that from more than 9,000 strings after executing the script, we will get 11,000 strings. And it's the same what you can see here, that before the concat string function is called, it's much easier for reverse engineer to look at the code, and right there you can see the script, the string that we were just defining. So this is very similar for other architectures. Let's take a quick look at the ARM 32-bit architecture. Before we execute the script, this is how it looks like. The difference that there is not directly the address of the string that we are looking for that is placed to the register. Rather, there is a pointer used which will point to the address of the string. So there is one extra step here, but after that it's very similar. Then we will also place all this information onto the stack before we call the concat string function along with the length of the string. So once we execute our script, we can see that the pointer will be really nicely renamed. As well, the string will be defined, so it will be first much easier to read the assembly code, and second, much easier to find the strings through the defined string window. And as a next step, let's take a look at the 64-bit versions. Already here we have two different solutions. In the first one, the instruction called OR is used, while in the second one, move. Basically, they are doing the same, just a little bit different. And here we also look for these sequence of instructions. And after we execute our script, we can see that these strings are nicely defined, so reverse engineering becomes much more easier. If someone is interested and want to understand it in more details, then you can use the example binaries that we put on every single slide, so you can see what we used for that specific test. So let's turn to the challenges here. Obviously, biggest challenge that we have to create for every instruction set a different part in the script, and even within one architecture can be implemented in many ways as we have seen in the previous slide. And obviously, if someone wants to break it, it's very easy. Here, for example, the length was already placed into the specific register, and that's why the sequence of the instructions are not what we would expect, so our script couldn't define the strings. So we have to keep an eye on it and update the script as we see new solutions coming up. So now that we talked about the dynamically allocated string structures, let's take a look at the statically allocated string structures. Basically here what we want to do is look for a series of pointers to the string followed by a possible length value. Obviously there are many possibilities to have false positives here, so we wanted to limit these. So we limited the length of the string, we searched only for printable characters and check only in data sections. This is not architecture specific. Obviously, it matters if it's a 32 or 64-bit binary, but other than that, it works the same for the different architectures. So here in this example, you can see that there are string pointers followed by string lengths. And the first pointer was successfully identified by Ghidra, as this is directly referenced from the code. But after executing our script, we will define the other pointers as well. And if we follow these pointers, we can see that the strings are not defined either. So this is what we also want to achieve with the script. So once we execute the script, it will define the pointers and the integers and the strings as well. So it will also help a lot in reverse engineering to find these specific strings that are interesting during our analysis. So what are the challenges here? First of all, as I already said before, we wanted to eliminate false positives, so we only used search for printable characters, but obviously it's possible that we are looking for something that contains non-printable characters as well. It's a very small part of the script, so if you want to use it, just experiment with it, change the values, and find what is the best for your analysis. And the same goes for the string length limitation. So it can miss some of the strings if they are larger. So this can also be very easily changed. So these are not very big problems, but we have to be aware that some of the strings might be missing because of these limitations. Another challenge when we are working with the string recovery is when Ghidra is falsely defined some data types. So what our scripts are doing, looking for the string values along with the lengths and create pointers, define the strings and create the integers. But what happens if Ghidra, for some reason, already defined data? So for example, here you can see that these values, the 39, 13, 8, that we would expect to be an integer, to be the length of the string, are already defined. It's kind of funny that it's called undefined, but it's still a defined data type. So when we look for these values and we want to define an integer there, we will get an error since we cannot create a data type where there is already a data type. So what our script is doing, first we will remove this data, the undefined 4 and undefined 8 data, and then we will redefine it to create an integer data type. So after executing the script, this is what we will see. The undefined will be changed to integer, and the pointers and strings can be also created. Obviously, it can happen that there are other data types created by Ghidra. So for example, here we can see that there is a large string blob defined as one string. There are multiple smaller strings that are concatenated, and there is somewhere the null termination character, and Ghidra defined this as a whole one string. And you can see here that there are offcut references, meaning there are references within the code to some parts of the string, not the beginning, but somewhere in the middle. So here, the solution could be to undefine this string and then define the specific parts one by one. We are still testing this. It's not in the script at the moment, but there is one solution that you could use. When you look at the defined strings window, there is a possibility to see, first of all, how uh, long those strings are and how many offcut references are there, meaning how many references to the middle of the string. So if you see something like this, when there are many references to different parts of the string, then you can assume that that was a falsely defined data type, and manually it's possible to undefine. So it's also not something very difficult to do. And another challenge was and it still is, the compiler view. So even when we could define the strings, and as you can see on the left side, this is the listing view in the assembly. It looks very nice. There is the string that we wanted to create readme for decrypt.txt, so we can read it easily. On the other hand, in the decompile window, there is a huge string because it cannot really handle strings with fixed length. So it will show the string until it finds a null character, even if we define the string in a way that we explicitly said the length. Luckily, it will be solved for the next release. So if you use Ghidra 9.2, then you will be seeing the correct string values. And obviously there are many more possibilities and many other interesting information that we can extract from Go binaries. And we have many plans how to continue our work. This was mainly an introduction into the quick wins. How can we recover functions? How can we recover strings? First of all, obviously, we have to work on the string recovery script, including further architectures and keeping up if anything new is coming up or any changes happening. The other interesting thing is to recover function arguments and return values. As you have seen before a function call, these arguments are placed onto the stack and the return values are also moved to the stack, not to registers as we would expect. So for example, we cannot look for the EAX register for the return value, rather we have to look for the stack. And Ghidra has a hard time identifying these arguments and return values correctly. So for example, on this slide, you can see this addition function, which expects integers, and the result will be obviously also an integer. And these types, identifying these types, Ghidra has a hard time. But as part of our other planned enhancement, we are aiming to create a script which can recover types because descriptions for the different Go types are available within the binary, even in the stripped binary. There are basic types that you all know, string, bool, numeric types, and also composite types. But what is very interesting that you can find the developer defined types within the Go binaries. So for example, here the main.info struct, this is also from the EcoRoix ransomware. This structure consists of the RSA public key and the README string, which is also very helpful when we would like to understand and doing the reverse engineering, what kind of information, what kind of types are there, structures, and this all can be found within the binary, and this is one of our future goals to recover these types. Obviously, we are not the first one who are working with reverse engineering Golang binaries. There are already a lot of work done, especially with other tools like IDA or Radar 2. Also, there are scripts for Ghidra, so feel free to look at these, go through these, and play with them as well. And here you can find the list of the files that we used during our research and our presentation. We will upload these Hello World examples to our GitHub repository. So if you would like to follow the different steps or experiment with the scripts, then you can use the same files, and that can help in understanding how this whole um, string recovery or function name recovery is built up. And there are many other researchers creating very good presentations and write-ups about the Go malware research topic. Just 1 month ago on the Radar conference, there was a very interesting talk about how to analyze Go binaries with Radar 2, so I recommend to read through these as well. And thank you very much for your attention. I hope you all enjoyed our presentation and could learn something from it. Please feel free to ask questions. We are also very happy if you contribute to our research. You can find us on Twitter, also our research group, and this is where this is our GitHub repository here where you can find all the scripts and the presentation and the materials that we used. So enjoy the rest of the day and the rest of the conference. Thank you.